All right, I am back with the backside. Sorry, I couldn't resist. Okay, so on the front we talked about this power rule, but I'm just going to put it in complete mathematical notation for you, okay? And so the power rule says that if I'm going to integrate, okay, take the antiderivative of x to the n dx, I would add 1 to the exponent and divide by that new exponent. And then again, I need this plus c. Right, when I go backwards and check this, right, I could take the derivative of this and I should land with that x to the n. The derivative of any constant is 0, meaning I just have that x to the n. For all exponents, right, n is an exponent, that are not -1. And that's actually going to be the issue that we are going to deal with in part F. Okay, I'm going to just make an adjustment to this. And so on the front, we said if I had a x to the n dx, that the antiderivative would be a x to the n plus 1 divided by n plus 1, okay, plus c. So if I have a coefficient, it doesn't change anything. That coefficient just comes along with that particular part of the function. Okay, so for example, if I said integrate x cubed or find the antiderivative of x cubed, I would add 1 to the exponent and divide by the new exponent plus c. And by the way, x to the 4th divided by 4 is the same as saying 1/4 x to the 4th. And so you can write that either way. All right, similar story. If I'm integrating or finding the antiderivative of x to the 2/5, I would have to add 1. And again, I like to write that as 5/5, right? That's going to give me x to the 7/5. And I divide by that new exponent. But that kind of looks gross, right? Like we don't like to leave answers with complex fractions. So dividing by 7/5 is the same as multiplying by the reciprocal. And then again, don't forget that plus c. Okay, so again, those are just examples from the power rule for integrals, and we worked on that on the front side. So let's take a look at part F. Part F says, and find the antiderivative of y equals 1/x. Okay, now, when I talk about 1/x, that's the same as saying x to the -1, right? I could write 1/x as x to the -1, which is why we said up here for the power rule, that the power rule works for all exponents except -1, because there's an exception. All right, so the function capital F of x, remember f of x is an antiderivative. Capital F of x is an antiderivative. So capital F of x, the antiderivative is natural log absolute value of x for this function, okay? For all mean values that are not equal to 0. So here's the rule. It says if I'm going to integrate 1/x dx, the antiderivative of 1/x is natural log of the absolute value of x plus c. And I'm going to write this a slightly different way, okay? I can say, or if I'm going to integrate x to the -1 dx, right? That's the same as 1/x. Then again, the antiderivative is the natural log function, natural log of the absolute value of x, don't forget plus c. So let me talk about this particular example. It says that I need to integrate 4 divided by x dx. And some of us might not recognize that the antiderivative is going to consist of the natural log function. So let me talk about different ways that we could write this integral. This could be written as 4 times 1/x dx. Those two things are equivalent. The 4 divided by x, or 4 times 1/x. Another equivalent form for the integral would be 4 times x to the -1 dx. That's an equivalent form of this. And in these two equivalent forms, it might be easier for you to identify that the answer of this antiderivative would then be, well, the 4 comes along for the ride, okay, times the natural log of the absolute value of x plus c. It's just that sometimes when we see that notation singularly, that 1 divided by x, or that notation x to the -1, it cues in my brain that the antiderivative is the natural log of x. Okay, These next two properties are properties that we have seen with the definite integrals. Remember, a definite integral is where I have those a to b limits. And the idea here, right, is that if I am integrating a function, two functions being added or subtracted, I can integrate them individually. And multiples, again, means that if I'm integrating a function that has a coefficient, I could pull that coefficient out. That actually happens up here. I could have written this as 4 and then take the antiderivative of x to the negative 1 dx. So again, that 4 came along for the ride, and the antiderivative was the natural log of the absolute value of x plus c. We saw that when we talked about definite integral properties the other day. All right, let's talk about e to the x next. And so e to the x is one of my favorite functions because the derivative of e to the x is e to the x, and the antiderivative of e to the x is also itself plus c. All right, so I'm going to use my, my properties to pull this apart. So I see that I have a 3e to the x and a minus 4. So I can pull the 3 out. That's a coefficient. I'm going to integrate e to the x dx minus, then I'm going to integrate 4 dx. Okay, so the 3 comes along for the ride. The antiderivative of e to the x is e to the x minus. Okay, so 4, remember, the power rule says that if I have a polynomial, technically I do, I have 4x to the 0. If I have a polynomial, I can add 1 to the exponent and divide my coefficient by 1 in this particular case because my new exponent is 1, and then plus c. Okay? All right, the trig integrals. And so I know we all get a little nervous when we see the trig integrals or trig of any kind. And so what I want to just, kind of mark out for you is that you're not taking the antiderivative of the 6 trig functions. You're taking the antiderivative of the derivatives of the 6 trig functions, right? So it's like saying the derivative of what gives me cosine, okay? The derivative of cosine is what? Well, the derivative of cosine is really negative sine. We keep the negative out. The derivative of sine is cosine. So that's what I would integrate is cosine. The derivative of tangent is secant squared. So I would integrate secant squared to get tangent, to go backwards, right? The derivative of cosecant is cosecant cotangent with a negative. Okay, so you see that negative floating in either location. The derivative of secant is secant tangent. So I would integrate secant tangent to get secant. All right. The derivative of cotangent is negative cosecant squared. And so I would integrate that cosecant squared to get the cotangent. Okay. So again, I'm just going to make this statement. Okay. You are integrating the 6 trig derivatives. So if you know what the 6 trig derivatives are, then you're going to go backwards to figure out what function did that derivative go with. Okay, you just have to be aware, though, of the negatives. Okay, so for example, I could rewrite 2, I'm going to integrate 2 cosine of x dx. So I can bring that 2 out. And what this is really saying is, what do I take the derivative of to get cosine? I take the derivative of sine to get cosine, use that 2, and then a plus c. Okay. So we are going to do more practice in class tomorrow using whiteboard problems or Pear Deck. So hopefully you took some good notes and you got all these properties down and you can use them as we practice.